You could. Writing a book is a lot of work, so PowerPoints are really, really good.
You can almost say PowerPoint is like it's kind of like getting all my processes.
Yeah, the fluff. So y'all know I published a book, right?
Yeah. My neighbor.
AT, doesn't turn on the projector. That always does. Sensor technology and applications is the name of the course. We'll do a little introduction here to the course. And then we'll get right into some of the sensors we'll look at. And then we'll go over and play around with the manufacturer line a little bit, see if we can figure out where these sensors, some of these sensors are. So what is a sensor? Also called a transducer, by the way. So those two terms are used interchangeable. So it depends on where you're at, what they want to call them. So transducers, or also called sensors. Of course, the name of this class is sensors. So what is a sensor? Yes. So a device that converts a physical stimuli into its electrical equipment. And today we'll look at something referred to as a transfer function. Basically, a transfer function is the ratio between the physical stimuli and the electrical quantity. So that would be taking something like PSI and converting it over to volts. Well, the transfer function would be, say, 100 millivolts equals to 1 PSI. That would be the transfer function. And once you learn the transfer function of the sensor, then of course you can calculate what you expect out of it, right? Does that make sense? So what are the 5 basic units? So we have sensors. We have tons of sensors. But a long time ago, they said, okay, we got 5 basic sensors. But over a while, they said, we got a lot more sensors than that. But what do our sensors do? It takes physical stimulus and converts it over to electrical signals that our brain processes. So what does our brain process? Our brain processes electricity, right? Y'all understand that? So our sensors and the sensors that we're doing in this class do basically the same thing. Right? Y'all understand that? So what are our 5 basic things? Sight, sound, smell, touch, and hear. Right? That's the 5 basic sensors. When we start looking at it, we say sight, but sight actually deals with 2 sensors. We have what we call cones, and we have what we call rods, right? You understand that? The cones detect black and white, and then the rods detect what? Color. But it only detects basically 3 colors. What are the 3 super prime colors? Red, green, and blue. So your rods can't detect black. But to get all the colors, we got to combine those colors and then combine an intensity with that, right? You understand? So your cones gives you the intensity, and then gives you the colors. So if we only had rods, we couldn't see black, because you can't make black with red, green, and blue, right? You understand? So we have 2 sensors that actually do our eyes. So here, though, y'all did real good on that. Y'all been taught this for a very, very long time. But when you read about the human senses, you'll find that humans can sense a lot of other things. What can we sense? What else can we sense? That would be a nervous response. What can we sense? So here we can't take an electrical quantity and convert a physical stimuli and convert it over to an electrical quantity. Yes, you could. Good point. What else? That's good. I don't have that in my list.
Pain.
Pain. We can sense pain, right? Which has nothing to do with touch. That's pain. What else can we can sense pressure, right? You understand? We're not talking about being emotional pressure. We're talking about pressure. You can tell that right off the bat when you go swimming and you start going underwater. You have a sense of that water, of that pressure. What else can we can sense temperature. So we know when it's hot outside and we know what it's cold outside, and our brain responds to the temperature, right? You understand that? If we get real cold, then the brain starts moving more blood into your brain, right? You understand that? We get real hot, then what do you start doing? You start sweating. It automatically responds to that. What else can we? Humidity?
Like moisture.
Yeah, moisture. We could probably sense that. What else? Sleepiness. What else? Mine's off. I have a problem with my accidents. We can sense motion, right? We can sense when things are in motion. We have balance. We can sense equilibrium. So we can balance. We can sense our even if I was totally blind, I know where my nose is. So just the location of my body parts, I know where those are at. So I can close my eyes, and that's why the police gives that, because this sense gets off if you're what? If you're intoxicated or impaired by a lot of different things. And that's one that they have you do, is they have you try to do what? Touch your toe, your nose, because we know where our nose is unless our brain is not working right. So that's one of your senses that alcohol and drugs affects is the location of your body part. You ever seen that? It's so funny, especially on those police videos where they have these people try to touch their nose. They'll be touching all over the place. But I have no problem. I know where my ears are. I know where everything's at, right? Equilibrium, balance. We have the ability to balance. By all practical purposes, our mass is all off. Your balance, when we try to do things to balance, we talk about the center of gravity. Our center of gravity is where? It's up high. Where we want our center of gravity to be in the middle of our mass, it's not in the middle. But yet we have the ability to balance on these little things that we call feet, right? You understand that? Which is a very, very complex. And that's one of my senses that was affected by my gravity. So temperature, some of y'all got that. Proprioception, sense of the water, location of your body. So we have that sense. We can sense pain. Somebody says that. Equilibrium, which is balance, motion, gravity. Somebody said pressure, but we can actually sense gravity, right? Which would be our weight. Pressure, that was brought up. Hunger. Well, I didn't bring that up. You have a sense of what? Hunger. You know when you're hungry. Your stomach knows when it's hurt. It starts, we say my stomach's growling, but it lets you know when you need to feed it. Thirst, which we didn't bring up. So everybody has a sense of thirst. So you know when you need to do what? When you need to drink. Nausea, nobody brought that up. We know when we need to get rid of stuff that's not right in our stomach, right? You understand? We have those senses that we know that. We can sense stretch. We have stretch receptors in our lungs and our stomach. So we know when we're full. We know when we had enough to eat. Some of us do. So these are all the sensors that I looked up. But there's some good ones, that we came up that would still be fall into human senses. So we talk about the 5 basic senses, but we are amazing things, right? You understand? They've just evolved, right? Sure. Like my cell phone. My cell phone has evolved. Okay, everybody okay? So when we get into digital sensors or electrical sensors, they do basically the same thing as our sensors do. But we have 2 types, basically 2 categories. We have what we call analog sensors. So what is analog? This is a pretty good explanation. This is a continuously varying quantity, right? You don't understand that. Now, of course, electricity, we got three quantities we can vary. What are the three quantities we could vary? Ohm's law, guys. Resistance, opposition, current, or both. Now, what's the resistance is hard to see in from one place to the other. So the two primary things that we use in analog sensors are what? Voltage or current. Of course, the predominant right now is voltage. Voltage or current, the advantage is what? A lot of people think digital is more accurate than analog, but that is totally false. Analog is by far more, because in analog I can deal with infinity, right? You understand? I cannot deal with an infinite number. But when my temperature, and what's the high today? So if it was digital, it would go from the low to the high instantly. And that's all, that's impossible to do. Right? You understand that? But it varies. It varies an infinite number between the low and the high. There is actually an infinite number of incremental changes. Of course, we drop it down into degrees, but you got to understand, we have thousands of degrees and millions of degrees, and it varies gradually and because it's analog. So temperature is analog. Right? You understand? Sunshine is analog. Days are analog. Right? You understand? We say 24 hours of the day, but then we can take that and subdivide it into what? Minutes or hours, or hours, minutes, seconds, but we say seconds, and that's the smallest unit that a lot of people deal with, but it actually varies an infinite number of changes for every second, right? You understand that? We just can't comprehend that. Requires less bandwidth. Bandwidth is a term, anybody know what bandwidth is? Yeah, what is media? First, to understand bandwidth, we got to understand media. So we're trying to send information. We're trying to get it from our sensors up to our brain, right? You understand? So we have to send this information through what we call media, and they call it neurons, or right? Right. Well, we transfer it from one to the other. It's really, really neat the way we work. But in electricity, we're going to send this through conductors. They're either going to be copper, that's not true. We're going to send it either through the air, right? You understand that, using radio frequencies, or we're going to send it through conductors, copper wire, or we're going to send it through fiber. That's the three predominant ways that we do what? We transfer information through media. Well, every media has a bandwidth. And the bandwidth is the range. So media is what information flows through. It's not the information, it's what information flows through. Right? Y'all understand that? And every media has a range of frequencies that it can reliably pass. And that's what we call the what? The bandwidth. Well, not really. So air can handle a certain frequency. We're not temperature didn't deal with frequency. It deals what is frequency? Frequency is a signal that's changing or something that's changing at a certain rate. Right? You understand that? We generate to send electrical information. We start dealing with the band. So DC has no bandwidth. So the only thing that limits the amount of DC current I can send through a media. So we can't send DC through the air. Everybody understand that? So if we're going to send DC, we're going to send it through a metal conductor. But what limits the amount of DC you can send is the resistance of the conductor. Because if I'm trying to send something using voltage, well, we can't have voltage without current, right? You understand that? If I've got current, then I've got resistance, and then I have voltage drop. So how much limits the amount of information you can send to an electrical conductor is how much current are you trying to push and how much resistance does the conductor have. Now when we start placing that or trying to do frequency, we got two other things that fall into play. We have something called inductance and we have something called capacitance that we don't run into in DC. Now what these do, these guys vary with opposition. Vary with frequency. So how far you can send an AC signal depends to a media, depends on how much inductance and how much capacitance you have in the system, right? Plus how much resistance you have. So in AC, we're dealing with three types of resistance. We're dealing, well, actually two types of opposition. We're dealing with what we call resistance, and we're dealing with something we call reactance. And they call it reactance because it reacts to frequency. That makes sense. So the bandwidth would be the range of frequencies we could send through that media and still get a certain amount of power to the other end. Normally the cutoff is, now current, of the three quantities, the two that we most often measure, of course, are resistance and voltage. And why is current not in there? Well, current is a flow. And to measure a flow, that means we have to break the circuit and put a meter and make the current flow through it, right? So when we talk about power, and this is a little beyond the scope of this course, but it's okay. So normally what we do when we look at bandwidth, is they draw what they call a curve. And when we start looking at a bandwidth, normally a bandwidth curve kind of looks like this, where they'll have V. And this is V to the load. And then down here they'll have F, which is frequency. And something that has a bandwidth, we would start off by almost not passing anything to the load. And then all of a sudden the load would go up, and then it would level off. And eventually it would drop down. Now sometimes it has a frequency of 0, it would pass everything, which is pretty neat. And what we're looking at is we're looking at 70.7% of your maximum voltage. 0.707, which would be 70.7%. Now how they come up with this number is very interesting. But remember, I is equal to V over R, right? Y'all understand that? So what happens if your opposition doesn't change and your voltage goes up, your current goes up proportionally. So we say that voltage and current are proportional. So that means if I was going to come up and let's say I had my power, I had 10 volts at 10 amps, then that would give me 100 watts of power. All right, you understand? Now let's reduce that by 70.7%. So power would equal to 0.707, and why I do this is so now 0.707 is actually rounded. This is actually the reciprocal of the square root of 2. So the square root of 2 is 1.414. 14141414. So if you took the reciprocal of that, you'd come up with 0.707 and you'd start repeating. So we'll get pretty close this way. And then I would 0.707. Well, what would the power be now? It would be like, it calculates to be like 49.9 watts, which actually is what? 50 watts. So when my voltage drops down to 70.7%, it means my power has dropped down by what? 1/2. So we call this the cutoff. This is the cutoff frequency. So when we deal with bandwidth, maximum bandwidth, now what we'll do when we transmit information is we'll take the maximum bandwidth and we'll subdivide it down into the assigned bandwidth, if that makes sense. And so when you talk about your bandwidth is a portion of a overall bandwidth of the media. Y'all understand that? So that's how, so bandwidth has two terms. It's the range, truly a bandwidth is the range of frequencies that a media can reliably pass. Then we have what we call basically assigned bandwidth. And that's how much bandwidth your internet service provider assigns you. But it can never be what? More than the maximum bandwidth. In fact, it's a lot less. So, maybe, so that's 70.7% would be what we call bandwidth. Well, analog, digital takes a lot of bandwidth. And why? Because if I've got an analog signal like AC, it's changing like this. A digital signal changes like this. And we're talking about a frequency here that we just can't understand. We call it the rise time. And the rise time is going to be in nanoseconds. And basically, frequency is how fast something basically changes. So digital, sending different digital information, just going from 1 and 0 and a 0 to a 1 and a 1 to a 0 takes a lot of bandwidth. I mean, digital takes more bandwidth. So it limits how much information we can send, right? So a media that might handle, 100 megahertz might only handle 15 megabits, which would be good. So this is one big advantage of analog. So what are the disadvantages of analog? So it requires less bandwidth and it's a lower cost. What's the disadvantage? Since we normally use voltage is just very susceptible to what we call electromagnetic interference. So it's almost impossible to keep EMI out of analog systems. Digital, we can ignore it. Analog is almost impossible. So we have to filter it out. Try to do it. Yeah. Of course, I don't know. I don't have my headset over here, so you'll have to have a set of headphones. This is a big problem we have right here. Is digital, we can store it and use it later. Analog is almost impossible to store. Don't understand it. So how hard would it be to be able to store an infinite number of combinations? Very hard. Which means it's harder to interpret. Yeah, well, we'll talk about that transfer function. Once you understand the transfer function, then the Arduino will make a lot of sense. Digital and physical quantities vary in discrete steps. Normally for digital we use watt. So we have an analog transmission terminology called a current loop, where they use it's like a 10 to 20 milliamp current loop. And so what the signal is only very, and what advantage does the current loop have over a voltage loop? It's hard for electromagnetic interference to generate a current. But what you're dealing with is you're dealing with a low impedance circuit or low resistance circuit to handle currents, right? You understand that? And so it means it's more expensive. But a lot of industry uses what they call a current loop for their instrumentation. Digital is predominantly voltage. Easier to process with a digital computer. So if I'm going to process information with a computer, computers now are digital, right? You understand? So digital computers don't process analog information. They process what? Digital information. Yeah, if we're going to process it with a computer, somehow we're going to have to convert it over. So it's easier to transmit. So the analogy we use is that I'm over there on the hill over there and I'm trying to send you an intensity of light. And you're trying to interpret the information. And we are extremely smart, right? You understand? And you're trying to interpret information by the intensity of the light. That's analog. Digital, you're trying to see if the light is on or off. So how far can you tell if the light is on or off? If you can see the light, you can tell if it's what? On or off. The light travels a pretty good deal. So it's easier to transmit. Resolution depends on the number of steps of the binary bits. That's accurate. So somewhere we're going to have to give up. So what we're going to do now, instead of representing an infinite combination, we're going to specify a number that we're going to go to. And you cannot exceed that number. And the more higher resolution or accuracy we have, the bigger the number, which means it's going to occupy more storage space and it's going to be harder to process, right? So y'all can understand we're talking about microprocessors, and now we're doing a 64-bit processor. So that means they can process information up to 64 bits. Right? You understand that? Well, that's not, we can combine it too. If you're in the program, you understand you can combine those numbers. So if I'm going to deal with a lot of our sensors are analog, so if I'm going to sense temperature, the sensor is going to have to be what? Analog. But I'm going to have to run that analog sensor into a computer, which means I'm going to have to convert it from what? Analog to digital. So we have what we call DACs, digital analog converters. And then we have ADCs, which is analog to digital. So if I'm going to control the speed of a motor, normally we have to control it with analog, right? You understand? But my computer is what? Digital. So we have to go both ways. So what we do on analog to digital is we're going to take an analog signal and we're going to convert it over to what we call data. So we're going to run it to an analog to digital converter. Now once we got it, but what determines how accurate it is the resolution of the analog to digital converter. So digital multimeters. Those are definitely have what in. So it's a digital multimeter, but you're measuring analog quantum. So what's inside that meter? Analog digital converter, right? You understand that. And of course, what we deal with these meters is we deal with what we call the number of counts. So we have 2,000 count meters, we have 4,000 count meters, and now we have 6,000 count meters. So a 6,000 count meter would have a better resolution and cost more money than a what? Than a 4,000 count, which would cost more than a 2,000 count. That's something to look at. So what's the application of the meter? And we have people that go out and buy $500-600 meters, and they get a guy bail with a what? A $50 meter. Because all they need is 2,000 counts. And you can tell these meters because of where they range. So if the meter ranges on 199, then it's a 2,000 count meter. 199.9. If it ranges on 4s, like 3,999, then it's a 4,000 count meter. If it ranges on 6s, then it's a what? It's a 6,000 count. But the resolution we have, how accurately we place these steps. So what happens is we come up here, we take this and we convert it over to a binary. And to understand binary, we're going to have to understand a little bit about binary. Anybody? So what's the base of binary? So base is basically the number of combinations we can have, right? So binary, we have bi, which is 2, which means every digit only has 2 combinations, or every number only has 2 combinations, which is a what? 0 or 1. Also, it tells us how the digits, what weight each digit has. So in base 10, what we learned is we learned units, right? We run tens, hundreds, thousands, 10,000, right? You understand? But what people don't understand is a decimal number, 8,176.53. What the base really indicates is what weight each digit holds. And what you do is you come up here and say, okay, what's the base? Well, this is the base is 10, so that means it has 10 combinations. What are the combinations? 0 to 9. Now, of course, here you're not trying to learn binary. We're just getting a little feel of this. Well, what it also tells us is it tells us the weight each one of these things hold. So what I do is I take the base. So this is truly what the base is. So this digit holds a weight of 6 times 10 to the 0. Well, any number raised to the 0 is 1. So that would be 6 times 1, and we call that units, right? You understand? This would hold a weight of 7 times 10 to the first. Well, any number raised to the first power is itself, so that holds a weight of 10. So that'd be 7 times 10. So the 7 holds a weight of what? 70. The 1 holds a weight of 10 squared, which would be 100. And 1 times 10 squared, or 1 times 100, would be 100, right? And this would hold a weight of 10 to the third, which is 1,000. So 8 times 1,000 means that 8 holds the weight of 8,000. And then if I add all those together, I come up and get with the total weight of the number. What would be the next one? 10 to the fourth, 10 to the fifth, 10 to the sixth, 10 to the seventh. Well, what about on this side? There to the minus. 10 to the minus first, minus second. So we learned this is 0.1. 10 to the minus second would be 0.01, right? So binary has a base of 2. So it means this digit right here holds a weight of 10. Oh, I unplugged my. Holds a weight of 10 to the what? 2 to the 0. What would this be? 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. Huh? Yeah, you would know. You're over here. I'm over here. So it's basically once you learn Norman system. So base 8 would be 8 to the 0, 8 to the first, 8 to the second, 8 to the third, right? Hexadecimal, which is base 16, would be 16 to the 0, 16 to the first, 16 to the second, 16 to the third, right? You understand? And once you understand this, then now you understand what the base is. A lot of people say the base is the number of combinations, but that's true. But it's more true to say that's the weight that each number holds. Now, what's nice about binary, we won't deal with fractions, even though fractions, when we have the binary point, then I put some more digits over here. This would be 2 to the minus 1, 2 to the minus 2, you understand that? So if I've got what's nice about binary is these weights of 2 actually double each time. So what I would do, instead of using these 2 to the 0, I would say any number raised to the 0 is 1, right? Any number raised to the first power is itself. So that would hold a weight of a decimal 2. Then all we do is we just double it. 2, 4, 8, 16, 32. 64, 128, 256, 512, 1,024, 2,040, 4,092. 3,192, 16,384, 13,568, 5,536. You can tell I've dealt with binary a long time. So that means this guy here, so to get the actual decimal weight, and the problem we have is that to get the decimal weight, we have to get it into decimal. To get a feel of the weight of the number, we need to convert this to decimal. Well, all we have to do is just add the digits that's got 1 in it, or add the decimal weight that's got 1 in it. So what would I add? I would add 32. I'm not going to add 16 because 0 times 16 is going to be what? Okay. Then I'd add what? I'd add 8 and I'd add 2, and by George, I'm through. So what would be the weight of this number? 42. So this would be the decimal equivalent of that number. So this is what we're dealing with. So we have 2 types of answers. So what we're going to do is if I've got an 8-bit ADD converter, that means that guy's got to represent everything along that analog scale using how many bits? 8 bits. Okay, y'all understand? Well, how many combinations binary numbers can we represent with 8 bits? Well, to get that, you just take the base and you raise it to the number of digits, so that would be 256. So that means I would have 256 combinations I could represent. So that means each one of those steps would represent a certain voltage level. And that's all we got. When we look at a digital signal, we'll see that it's going to move a digital to analog converter. It's going to move. It's not going to be nice and smooth. It's going to move in one steps. And I'll go get a scope when we take our break. We got a digital scope, and we're going to look at an analog signal, but the scope's going to display it in what? Little steps, because it's going through an analog to digital converter. It's a digital scope, right? You understand? So 256 steps. So if I was gonna, if the maximum I was gonna ever read would be 10 volts, then I could say, okay, 10 divided by 256, and this would be what we call the transfer function, and it's gonna be in volts per step. That makes sense? So what would I have? Anybody got their calculator? So what we did is we took a voltage quantity and moved it over to a digital quantity, right? And we call that transfer. Now give that to me in milli, 39 point. Yeah, usually we carry these out because it's got. Okay, ours 3. And we'd say millivolts per what? Per step. So now I could say, okay, what number would represent this? So what we're doing is we're taking this representation. Right? So if I say, okay, what would be the number represented by 5 volts? Well, I would take 5 and multiply by that, right? You understand? Which hopefully comes up to pretty close to 5 volts. So now the computer, instead of seeing 5 volts, it's going to see a binary number that represents 5 volts. But the resolution, so it's going to move in 256 steps, right? You understand? Well, what's it going to do between them? Well, it's going to either take it as, it's going to either go up to the next number or stay at this number. So the number of bits in A-to-D converter determines the resolution. I'm not sure. I think the Siemens has a 10-bit resolution, which means that it could take a unit and get 1024 divided into 1024, but still it's not going to be a perfect representation of the analog signal. Does that make sense? Because it's moving in what? It's moving in steps. And that's also when we go from digital to analog. So digital analog, what it's going to do, the digital is going to move it in what? Yeah. Steps. And then what we do is we can run it through a filter, an inductor, and we can filter all that out. What we have to do on variable speed drives, AC drives. So AC drives are generating digital signals out to that motor, but the motor don't want to see steps, it wants to see, so we run it through filter. So if you ever do any research on it, so our PLCs let's keep going. Everybody okay? So this is the basic control system. We're going to have what? Inputs, and then some type of control logic, and then we're going to generate what? Output. Now when you take motor controls, we're going to do what we call relay logic if you take motor control. And everybody's in here taking motor control, so we deal with relay. We move over to a PLC, your control logic is done by a computer. So it's basically the same setup, but you can say your PLC would be there in the center, right? And it's a computer. Now what advantage does relay have over computers? A lot cheaper and a lot faster, believe it or not. Now, what advantage does computers have over it? But if I want to change the logic, I have to change the circuit. So what advantage does computers have over relay? Well, we say it's cheaper, but in actuality, it depends on how much you got, right? If you would have saw, before they upgraded PLCs, number 4 galvanizing line, they have what we call relay houses. And you would walk into that thing, and it was unbelievable. One whole wall was nothing but relays. That did 90% of it was nothing but logic. And from what I understand, this was after Ridge. They came in and replaced all that relay logic with PLC. One PLC in that big old relay house. And we're talking about those relay houses was probably about half the size of length, and they were probably about 12, 15 feet wide. One whole wall was relays. Now that's a lot of money. They replaced it with a PLC. Now the problem is with PLCs is that if you want to change the program, if you want to change the logic, you change the program. The problem with relays, if you want to change the logic, you got to rewire it. You got to go in and take relays out or add relays or rewire the circuit you got. This is predominantly why PLCs are dominating, the amount of space they occupy. So relays occupy a lot of space. PLCs occupy a very small space. Right? You understand that? I'd hate to see the relay logic that would run these lines. If we get relay logic. So PLCs is the predominant control logic. They are the predominant logic in new applications. The problem is, if you go into a lot of plants that's been around for a long time, you're going to do what? You're going to see both. Because they have a tendency not to change things that's working. If they've got a system that's doing what it's supposed to do, they're not going to screw with it, right? Because it's making money. But if it's new stuff, then they're going to go out and they'll probably be a lot of PLCs. So you get in a company like U.S. Steel, which is bringing people back, by the way. You're going to run into both of them. A lot of relay logic and a lot of PLC. Where do sensors belong at? Yeah, they're over here. We have a lot of input devices, the sensors are all over there. So in a control system, guys, what would we want to sense? Some of the things, yeah, position. What's that? Quantity. Or we'll say just count. What else do we want to do? Color. Huh? Weight? Huh? 10? Height, size, height, speed. What else? Got any? What about you, James? Being quiet down there. What we might want to see? Huh? What we might want to see? Come up with something. Your turn. Just some in a control system might not what we might want to see. Distance. Yeah. All right, sound. Sound would probably be better than noise. Sound. Huh? Well, motion, yeah. Huh? Yeah, this is probably more position, because what position? Huh? Oh, sorry. Distance, height, pressure. Is that in there? Anything else? Light. Huh?
Current.
Yeah, we might want to sense current, might want to sense voltage. Power is a relative term. To sense power, we got to sense two things. We got to sense what? Voltage and current. It's hard to sense resistance. It's real easy to sense current or voltage. Huh? So let's see. Let's go back over. So position, just we gotta give that. Speed. This is one of them y'all came up with. We might want to sense weight or force, right? Okay. Count. Somebody came up with that. Pressure. We came up with that. Flow. Nobody came up with that. How fast fluids or liquids are moving. Yeah. Temperature. That's electrical though. Light. Somebody came up with that. Thickness. How thick something. That was very important, especially on a company that coats something. They want to constantly keep up with is that coating exactly what it's supposed to be. Thickness is supposed to be. US Steel, we had an X-ray gauge on number 4 galvanized line that kept up with the thickness of the galvanized coating that's on it. Time, nobody said that. Oh, we did? Gases. Liquid level, somebody said that, which is pretty good. Motion, we talked about that. Orientation, how it's positioned, right, or oriented, which is becoming very, very popular with vision systems. Shape and size, how big something is and the size it is, right? Proximity, if it's, we're going to find out there's a difference between, so normally when we say position sensor, this is going to sense where the thing's at over a range. Right. Proximity means it's going to be at a what? At a spot. Proximity means it's going to be at a certain position. Position sensor says it's somewhere in this range. Okay. Moisture. I might say that humidity, which would be good. Viscosity, how thick things are. And this could go on, man. Just about anything that we can sense, except for maybe nausea and stuff like that, we can design a sensor to do this, right? Y'all understand? We have all types of sensors. Sense magnets. We have sensors that sense magnets, magnetic fields. On the planes I worked on in the Navy, they called it MAD, magnetic anomaly detector. And these things actually rode the surface, actually sense the magnetic flux of the Earth. And every time a submarine would be underwater, what would it do? A big chunk of metal, what would it call the flux of the Earth to be? It would concentrate through the sub. And that was one of the main things that that was ISASW, worked on anti-submarine warfare plane. And that was one of our main sensors to know where to drop the torpedoes. The nukes. The plane I worked on was nuclear capable. We carried the Mach 45 or nuclear torpedoes. What we'll look at first, after y'all take y'all's break, is we'll look at what? Position. Okay, guys, y'all take a break. Yeah, make sure everybody on this. Hey, Barry. Glad you can make it, man. Make sure I get you on roll because I've already called it. Nah, I'm not gonna be able to. I could probably figure it out. Different potential, different. Some of y'all that's had this before. I feel like some of y'all potentiometers, optical rotary encoders, linear optical recoders, variable differential transformers, photoelectric, ultrasonic, and vision. The photoelectric, ultrasonic, and vision we'll look at in later lectures. So what we're going to look at here is the first four. Okay?
These are analog, correct?
Yes. Most of your sensors are analog. The actual sensing element itself is analog. I don't know if very few sensors, the actual element is, because they're sensing physical quantities. Now, proximity sensors could be digital, but yeah, they could be, but there probably could be analog. It's just that we'll talk about in a minute what they go through. So a lot of your sensors, the actual sensing element itself is analog. But it has a built-in A to D converter, single bit A to D converter. So a while ago we talked about representing an analog quantity with a number. A lot of times all we're trying to do is switch it at a certain voltage. And that way we don't have to have these 8-bit analog to digital converter. We got 1-bit analog, we got 1-bit analog to digital converter. They either say it's above a voltage or it's what? Below, or above what they sense or below what they sense. And but most of the time that's okay. And most of these have has a little span or adjustment on it where you can adjust where the switch occurs, where the A to D converter switches. Okay, just about all of them do. So the sensing element itself, probably, in my mind, I can't picture any of them that's not analog. So even light sensors, they sense a light, right? And the sensor itself does not do the switching. The sensor itself switches light. And what is light? Yeah, light that it senses, analog light, because not only does it have a color, it's also got a what? It's got an intensity. So potentiometers. We look at audio tapered. We have two types. So if you're going to buy these things, audio tapered pots. So when you look at a sheet, they talk about audio tapered and linear tapered. The problem is a linear means what does linear mean? Yeah, it moves in a straight line. Right, you understand. So a pod, if it's a linear tapered pod, that means you could tell about what opposition you would get out of the second pin depending on how many degrees it turns, right? Audio is non-linear. So the volume control on your stereo or your radio is non-linear because the human ear is not linear. First of all, we have a bandwidth, but it takes a power, it takes an increase by a decibel before we can detect a change in volume. So our ears does not hear. So your potentiometers or whatever you're doing to control your volume on your radio is not a linear device. Because if I turn it halfway, I want it to be half volume. Right, you understand. If it's a linear taper pot, you wouldn't get that. When we use pots for position sensors, when we're trying to detect the position, we make sure you get what we call a linear taper pot. So we have 3 connections to the potentiometer. And normally we number them 1, 2, 3. So our pot we can see coming out the side. So this is a rotary pot. We have 3 connections. And normally we number these 1, 2, and 3. So the center would always be what? 2. Are we okay? And then of course we have linear pots, which basically also called sliders, which would still have what? Which still have 3. Now what we do is we have a resistor inside these things. And this would be 1 and 3. So this is a 10K pod. If you had it in your hands, if you put an ohm meter between 1 and 3, it would measure 10K, no matter where position you had that knob in. Okay, y'all understand that? Yes or no? Now what varies is the resistance between lead number 2 or connection number 2 So when I start moving this thing up, what we're looking at, we got two options, or three options. And so what we do is we put this, and this right here is called a wiper, because it literally wipes across that resistor. So that's called a wiper. Okay, y'all understand this so far? Now, we could put that wiper up here, right? You understand? So what we would do, if I put an ohm meter right there, and then I put the other lead down here, if it's a 10K pot, it would measure 10K ohms. Y'all understand? If I move that wiper down to here, then it's going to measure 0. Well, what if I move it somewhere in the center? Well, if I move it away from the ends, what we end up with is this. And my wiper is going to be right here. So if this is 1K, then this down here would be what? 9K. But the sum from up here, if I measure across there, it's going to always measure what? 10K. Okay, y'all understand? So this ratio between these two resistors varies depending on where I have the wiper. That makes sense? Yes or no? So what we end up with is if I come up here and put this to a voltage, 10 volts, if I put the wiper all the way up, I get 10 volts. If I turn it all the way to the other direction, I get 0 volts. If I turn it somewhere in the center, we're going to get a voltage somewhere between what? 10 volts and 0 volts, depending on the position of the wiper. Now here, if this is 10 volts, then this right here would drop 9/10, and this right here would drop 1/10. So I would, if I take my reading across here, then I would show 9 volts, right? You understand? That makes sense. So literally, this is what we call a variable voltage divider. So I can get a voltage out of this thing. How many combinations? Well, basically an infinite number of combinations if you're good enough. It's real hard to do. Anywhere between what you put on the top and what you put on the bottom. The voltage available on the top and the voltage available on the bottom. Okay, y'all understand that? Now, what if we attach that wiper to something that's in motion? Well, then that wiper, that voltage I get out, is going to represent the position of that divider. Now, I haven't got this working yet, but you can see what we've done here. So what we've got is, I've got a, because it's got to have a minus, because the motor's got to turn different directions. You see, this is kind of fundamental, where I've got a potentiometer taped to the output of the DC motor. So when the motor turns, that pot gives me a voltage that represents the motor's position. So basically, the setup of the circuit, once I figure it out. Normally, when we deal with this, is what we're going to deal with is we're going to deal with something called an error amplifier. So that little old integrated circuit that you see inside is the error amplifier. So what I've got coming into one input of the error amplifier is I have a pot on there, a little old tiny one. And I think I'm using 15 volts. And I'm using plus 15 and minus 15. And then my wiper. And then coming back off the motor, it has a pot that's hooked up to plus 15 and minus 15. But what's controlling this is the what? Is the motor. So what the error amplifier does, if I come up here and put plus 5 volts, then the motor is going to turn until they have no error. So the output of the error amplifier is going to run the motor. So when this gets back to plus 5 volts, the error amplifier says, okay, the motor's at that position, and what does the motor do? The motor stops. So this is an error amplifier. I shouldn't use that symbol, by the way, because Oh yeah, this this computer don't have screws, so when that so what it means is there's nothing to hold the video in there, so when I move away it doesn't. So we have if I put a -3, then of course the motor, this thing here would output a output that would drive the motor in the opposite direction. So that's why I can't figure out right now where the minus comes in. I can see the connection for the plus, so there's a wire that got pulled out somewhere. So that's the layout there. So really what we got is we got a error amplifier. And then we're bringing one pot in that I'm controlling. Then we're bringing in one pot is coming from the where? From the motor. And then we have a setup that looks like this where we have two transistors. And one of them is supposed to be connected to -15, the other is supposed to be connected to +15. And then the motor's connected right here. So one of these transistors turn on that tells the motor which direction to turn. This is the pot. This is the rotary pot like we have. Most of the ones we have in our lab are rotary pot. You can see why it's called a wiper. It literally just wipes across. I saw one, I might set this up, where a guy took an index card and used a pencil. So pencil, the carbon that we use in pencil is it's a semiconductor. And what they did is they just took a band and used pencil to make a band. They used two paper clips to clip onto the two ends. Then they had another paper clip that would slide across that pencil mark and change the resistance, so it made a pop. Pretty neat. If you take these things apart, they're very, very simple. A lot of times they'll use carbon. Okay. So this is pretty close to what, so these are different types of pots. We have multi-turn pots. So the pots we have are what they call single-turn pots, but we can't get a single turn out of them because your wiper cannot go across pin 2. So normally they've got a mechanical stop in there that limits the range that the pot could run, usually around 350 degrees. So they call it a single turn pot, but you cannot make a single turn with it because pin 2's got to come out, right? That makes sense? Which is the wiper. Multi-turn pots, of course, we have what we call 10-turn pots. I've seen 50-turn pots where these suckers are, you can actually do what? You can really turn them. And of course, this right here would be a slide pot. We have some of these somewhere I have to show you. But normally these are slide pots, and what you do is it has a screw gear in here that turn this with a little pair of newer screwdrivers. It just causes this thing to slide back and forth. These are called, most of these are either 15 or 10-turn pots. But then what I'm going to do is I'm going to take this thing. So this is a pretty good animated GIF to show you. On the slide, what this thing does is move the wiper. Something's moving the wiper. Of course, you're moving the wiper with what? But you got to understand, anything that creates a rotary motion could do what? Moving this wiper. Or I could take a rack and pinion, which means I could put a gear here and then move a linear gear right here and still sense position even on something that's moving in a linear motion, right? That's pretty good. That's pretty good, right? So you see the ratio of the resistors are what's 2 and 1. Yeah, so if I put a voltage across this, then what you're doing is you're getting a ratio of that voltage depending on the position of the pot. Make sense? This is the kind of the setup I have here. We're a 350 degree pot. Motors can never turn more than 300 amps of what we call 175 degrees, we got 10 volts, it should take a while. So what should I expect if I put it at 30 degrees? Well, it's a 350 degree pot. You know, how much voltage do we have available to us? 10. So how would I do the transfer function? So the transfer function would be the maximum voltage I could ever get, 10, divided by the number of degrees available, 350. So what would my transfer function be? You got your calculator. Well, I need a number. 3 millivolts, which is good enough. But that's 3 millivolts per degree. So I set it at 15 degrees. So that means my V output voltage would be equal to, what did I say, 30 times 3 millivolts. So I get 90 millivolts out. So now I know, now I can measure a voltage and relate it to a degree, right? You understand? Or we say, okay, when my thing moves 3 inches, my pot moves 30 degrees, then we can go from, right? We can say, okay, 3 inches would be, then we could get what? Volts per inch, right? You understand that? So now, 30. So that would be 900 millivolts. I thought that was kind of low, but I went. Nobody else said anything either. 30 millivolts, so that would be what? 900 millivolts, which means now the pot is at 30 degrees. Right? You understand that? Yes or no? That makes sense? And this is what we call the transfer function. So now if I know I get, if I got 900 millivolts, I've got 30 degrees. Now I know I can actually get a voltage that represents a watt of degrees, and we call that the transfer function. Make sense? Yes? No? That's pretty close to what I have, except this is a lot further. Pot is supplied with 10 volts and is set to 82 degrees. The range of the single turn pot is 350 degrees. Calculate the output voltage, guys. So we already got the transfer function. What's the transfer function? 30 millivolts, right? Everybody understand how we got that? Yes or no? Answer yes or no. So what we do is we took what we're trying to convert it into. Well, we're trying to convert it into volts. So what you're trying to put, the electrical, what you're trying to convert it into, right? And then what are we going to convert it from? Well, you put what you're going to convert from on the input. So we put the maximum voltage divided by the maximum what we're trying to convert it from, right? You understand? And then I come up here and I say this equals, and it equals, and if you're going to be really accurate about this, you need to not round very much, right? So it's actually 28.57 millivolts. Or you don't use it, one thing might cause you a problem is you'll get an answer that's bigger than what's available. So if I say, okay, I've got 30 millivolts, I've got 350 degrees, you'll come up with 10 point something volts. So you can't get more than you put in. You can't get out more than you put in, right? So what would I do now? So 28.57 millivolts, which is really good. Usually 2 decimal points is okay once you get it. Then I would say, okay, my V out of the thing would be equal to what? 28.75 milli times 82 degrees. So what would my volts be? What's that? What is it supposed to be? Oh, 28.57 milli times what? 82. What did we get? What's that? 2.34. If you ever get more than this, you know you're wrong, right? You know you had to do something wrong. Because the maximum we can get out is, of the pod is what? What's at the top. Everybody understand that? I don't know what you mean by losses. Well, yes and no. And we'll talk about that in a second. The problem is we're going to have to hook this pot up to something. And the problem is, as soon as I hook it up to something, then we change this ratio a little bit. So what I hook it up to is going to have an R. So now we have what we call a loaded voltage divider. So yeah, this right here would be perfect. So odds are we're going to get a little less than that because when we load the pot. Everybody understand that? Even with a voltmeter. The bigger this R is, the less effect it'll have. And this is what we're talking about, loading errors. So what would happen, so normally if I came over here and set this to 5K, and then I set this to 5K, so I set my pot right in the center. If I have 10 volts, then what I would expect what? 5 volts. But if I come over here and put a 100 ohm resistor right there, then this is no longer a 5K. What would it be? I'm sorry, 100K. This no longer would be a 5K. What would this resistor down at the bottom be seen as? Come on, guys. What would this resistor down at the bottom be seen as? Huh? They're in parallel. I don't know. I mean, I got to calculate this. I can't pull this out of my head, right? Y'all understand that? So I'm going to calculate that. I'm going to say, okay, I got a 5K and I got a 100K in parallel. So I'm going to calculate this. So I'm going to say 5,000 reciprocal plus 100,000 reciprocal equals reciprocal. So it's going to see it as a 3,333.33 ohm resistor. So what would be the voltage? It can't be 5 volts. What would be the voltage? So it's a 3.33K ohm resistor. 3,333 ohms, 0.3. By the way, if you're going to carry it out to 2 decimal points, you might as well just go write it down, right? I see people carry it out. So now I got a voltage divider. I got a 5K right here. I got a 3,333 ohms right there, right? You understand? So what would be my voltage that I'm going to measure? We expected 5 volts, but it's not going to be 5 volts. It's going to be less. What would it be? Okay. So now I'm going to use what we call the voltage divider formula. So I'm going to say 3,333 ohms divided by 8,333 ohms times 10 volts, and this is what we would get out. We call it the voltage divider. So what would we get out? Well, I'm expecting 5, but what am I going to get out? 3.9. So we got 4 volts, and we expected what? 5. So once we load this pot, they call it the loading area. Once you put a load out there, then what's going to happen is your output is going, your transfer function is going to be a little different, right? So what determines that? Well, the higher that load is, now if we recalculate it to 10 meg, my calculated and my measure are probably going to be pretty dang close to the same, right? Instead of 5 volts, we might have 4.99, right? You understand? So this bigger the load is, the bigger this guy right here. So if you measure it with your voltmeter, most digital voltmeters have at least about 10 meg ohms worth of resistance on them. So odds are it will measure really accurate. So if you load this with anything less than that, then you won't have to worry about what we call loading. But still, it's going to be linear. Well, that's not true. But if it's linear, halfway would be half. It's not going to be half. So you'll go from 10 to 0, but in the center, it's not going to be quite linear. So it's going to have an error in it, right? If you understand the error, then you can understand it. Question? So pots. The big thing problem we have with pots is what we call a loading error. We're gonna have to hook something to the output of that pot, because if we don't, we're not measuring position, right? You understand what I'm saying? So if we hook this up to an A to D converter, we want that A to D converter to have an extremely high input resistance. Digital meters are real good because they got what? Probably around what? 10 meg. But they still load the circuit. A lot of people don't understand that. You think you can put a meter into a circuit without any consequences at all. That's not true. And the higher the resistance of the circuit, the more effect your meter will have on the circuit. We can take this and hook it up to gears, right? So down here, when this turns 90 degrees, the pod actually turns what? 370. It's called spur gear. So if we go from a big to a little, what do? A big gear to a little gear, what effect does that have? Yeah, we get less torque, more distance, or more speed. Good. Y'all know that. Of course, in troubleshooting, I'll have to learn that. In this class, we don't really know that. Analog to digital converters. We have one. I was going to try to look one up. By the way, during the summer, I'm on a half-time contract, which is basically 20 hours. You know how long I'm in class? 20 hours. The classes make 10 hours. So how many office hours do I have during the summer? None. So it's hard for me to come in here and do stuff. If you get here at 8 o'clock, I'll start with the door closing the right? But I was here though. I came early. So here we're this is our pot, right? You understand. This is coming into an AC converter. This is what we talked about a while ago. This is going to give us a binary number that represents the voltage. And if you get into PLCs, it's got an A to D converter on it. This is what you got to understand. Even though you're going to put a voltage in there, you're going to get a binary number that represents that number. And if it's a 10-bit A to D converter, that's going to divide that voltage into 1,024 combinations. That means you got 5 volts. Then the output of it should be around 512. It's not going to be 5 volts. It's going to be a number relative to the number of bits available to the A to D converter. This is why the meter don't use these A to D converters like it's going to be in a program of logic converter. The meter uses a counter. So what the meter does is it's really interesting. It uses what they call a zero cross detector. So what it does is it charges a capacitor up that represents the voltage you're trying to measure. And then when it takes it away, and then it does what they call integration. And it starts discharging, and while it's discharging that capacitor, a counter is counting until it crosses 0. When it crosses 0, it tells the counter to stop counting, and it displays that up on the screen. So that means it's not a binary number, it's literally a count. So it uses what they call a integration, integrator. So that's why they're rated in counts. Yellow. But if you get into a PLC or into a control system like this, then you're going to get a binary number that represents a count. And it's going to be a number that has nothing to do with what you're measuring, right? So you'll have to relate that 512 is actually half voltage. So you might power this pot up with 15 volts. Well, half would be 7.5, but it's still going to give you 512. So 512 would represent what? 7.5 volts. So that's what you got to do on a PLC when you say, okay, if this gets to here, I want to do this or that. You got to get that transfer function. Say, okay, this binary number represents this position, right? I understand that. So there's a little more to it. So these are the type of AD converters that a PLC uses. By the way, PLCs don't only come with AD converters. That's one of the things you have to buy. The 314 CPUs that we have has A to D on it. The 1200s that we just got, you have to buy the A to D converter and put it on it. These don't. I think the 1300s have D to A converters on them too, which is pretty neat. So these are pretty good PLCs. We'll go look at that. Encoders. We use these guys here a lot. So we're going to input these into a computer. Optical encoders give us digital information from the start. So they don't have to be what? I don't have to be converted. So I can take the output of these guys, here types, and I can bring them directly into a PLC without going through a what? A to D or D. So we have two categories. We have what we call absolute, and we have equal. Two subcategories. They can be either rotary or linear. This is what we call an absolute encoder. To understand this guy, you have to understand binary. This is counting in binary. It's binary. No hexadecimal too. It's hexadecimal on DNL. Now what it's doing on the right hand side is giving us it's not hex, it's binary. A lot of people get confused with hexadecimal. Hexadecimal, computers don't use hexadecimal. Has no idea what hexadecimal is. It's a way that we can represent binary numbers. So hexadecimal, we use hexadecimal basically in the code. So a computer understands that we have problems with binary. Because if I was to come up here and write a binary number down, let's write a 16-bit binary number. And I call this out to you. Okay, I said, okay, I didn't put this on the board. I said, okay, everybody, y'all write down this number, and I started saying 1 0 1 0 1 0 1 1 0 1 1 0 1 0 1 0 1 0 1 1 0 1. Everybody said, oh, right? Could you say that again? Well, this is what the computer understands. But what you got to understand is a computer can process information and turn on dots. So when we're looking at this is nothing but billions of little old tiny dots that the computer turns on, and it can turn on these dot patterns to do anything and make things appear like they actually are, right? So computers don't understand what hexadecimal is. I, as a programmer, understand hexadecimal. And when I'm writing a program, I can take these patterns and I can say, okay, this pattern represents this dot pattern, and I throw an F up there that represents a group of binaries. But the computer don't understand binary. Don't understand what? Hexadecimal. It has some knowledge of BCD. But if I was to come up here, not me, not the computer, if I was to come over here and come up here and I take this, and you don't, some of y'all might not understand this, but you can understand, and I'm going to come up here and I'm going to subdivide this down into groups of 4s. And I even said that wrong, so I missed some. Yeah, I don't have. Yeah, but I thought I was in 16, so you're right too. So I can't add bits over there. Well, I could, but it would change the weight of the number. So how many more bits do I need? Let's just open it. Well, yeah. I mean, it don't make it. I just need to go in groups of 4s. Well, not really. Let me take those off. So I'm just gonna throw some numbers up here. It don't really make any difference. How many I do? It don't really make any difference. I'm gonna come up here and I'm gonna start on the right, which I should have did before, but I took for granted. What? 1, 2, 3, 4. Well, the problem is there's no screw in right here. So every time I move my computer, what does it do? That cable unplugs. So there's really nothing I can. So if it starts changing colors or does that, it means that it's pulled out some. So y'all need to 1, 2, 3, 4. So if I was to go 1, I missed 1. So I was to go A, D6, B5. How many could write that down? If I said A, D6, B5, how many of y'all could write that down? Everybody, without making a mistake. So once you learn hexadecimal, you can go between the numbering systems really easy. But a computer don't understand hexadecimal. It's a programmer that understands hexadecimal. It says, okay, when I see this 4-bit pattern, turn on these patterns to make it display a pattern. So absolute encoders are not set up in hex, they're set up in binary. But I could very easily do this. So anytime the computer is going to display, or your PLC, if it's trying to deal with two big, really big binary numbers, odds are it's either going to use decimal, right? Most of the time it uses decimal, or it's going to use hexadecimal or octave. Octave is one which is the base level. And we can still run into this. So if I was to look at this stripe down here, this would be 0, right? You understand? And then I move over to here, this would be this pattern there, that pattern there, that pattern there. But it's all I got is 4, I got 4 bits. So 2 to the 4th only gives me 16 positions that I can represent. If I wanted to represent more positions, then I would have to add what we call more bands, right? So if I added another band, and I even make these bands smaller, which means they're going to be more, the detecting circuit is going to have to be smaller. One more band would give me 32 positions. So every band I add, I would get double the number of positions, but the bands are going to have to get smaller, right? And they're going to have to get closer together. So normally the way we detect these things is we use optics. We can go and look at the encoder on the FANUC robot. And normally what we do is we shoot light through there, so we have a light transmitter and a light receiver on the other side, and we shoot them through the bands. Now what's nice about an absolute encoder is that if I turn the system off and turn it back on, this guy's going to give me the absolute position of what I want to know. But it gets very, very complicated. These guys get very, very complicated the more positions I want to do. Right? You understand? Well, that's what we're going to look at the other guy. Well, it don't make any difference on these. You could lose the battery. You could take this sucker out and it could be at a certain position. And you could transfer it across the world. And when you go over and plug it in, it's going to know the position because this is what the big advantage of an absolute encoder. But I've only been able to represent 16 positions. So if I'm going to move 7 inches, then I'm not going to be able to do it, understand very precisely, because we're going to have so many bands per inch, right? You understand that? So that means, okay, this is approximately at this position. If I go to 32, we would have better resolution. right? You understand, but the notches are gonna have to be closer together, right? You understand, we're gonna have to have more band. And they're only good for one rotation. So they're limited in their range. I understand. So as soon as I hit this one right here, if it keeps turning, what does it do? It goes back to zero, and I think I'm back at the zero position. So this is an absolute encoder. This would be a linear on the side. So whatever we're trying to position, these are the detectors, so all it's doing is just showing you these things cover up, right? And all it's doing is counting in binary. But if I was to stop this thing, I don't think I can. Or maybe I can. Oops. No.
Yeah, 0.
Well, that's what's nice about it. It don't make. What do you mean backwards? Well, what it does is that we have the ability for if I'm going to sense the position of something, it's going to be either way, right? You understand? So counting backwards, it's going backwards. But every count would represent a position, whether it's moving what this direction or whether it's moving that direction. So backwards is a relative term. Going to 15 to 0. Well, then that would be counting up, or it could also what? Go down. But what's nice about an absolute encoder, so this has how many bands? This one has 1, 2, 3, 4, 5, 6 bands. So we could count to what? 64. Okay, makes sense. If I was to turn this thing off, and come back tomorrow, it would be the same place. We call these what? By the way, this is a binary code. This is using 5 here. This is counting in binary. Now, the problem we have with binary is that we have something in digital we call propagation delay. Propagation delay is how long it takes a count to propagate through the digital count. So the more number of bits that you have changed, the longer it's going to take for them to change. That makes sense? That would be like you flipping coins. So you put them all heads up, you flip one, it's going to take a certain amount of time. But if you have to flip two, you have to flip this one and that one, it's going to take a longer time. So the more coins you have to flip over from heads to tails, the longer it's going to take. And that's basically what's going on here. The problem we have with the binary code is when I go from 0 to 1, how many changed? When I go from 1 to 2, how many had to change? 2. When I go from a 2 to a 3, how many had to change? 1. When I go from a 3 to 4, how many had to change? 3. So you can see is the propagation varies with the count. So that means the more bits we have changed, the longer it's going to have to propagate through the counter. And so that means this would be limited how fast this thing can count, right? That makes sense. So what they did is they came out with a code called the gray code. So a gray code counter, and whether you understand it or not, so a code is when we use one thing to represent another. A gray code is used strictly for what? Counting. The advantage of the gray code is only one bit changes whether you're counting up or counting down. So this is an example of the gray code. Now this is a code. If I was to deal with this code a lot, odds are I would pick it up sooner or later. But right now, if I wanted to know what a 15 was, I would have to look it up in a chart. But you notice this it has nothing to do with the 1, 2, 4, 8. So this would be a 1. This would be a 0. This would be a 1. This would be a 2. This would be a 3. This would be a 4. But look how many bits change between a 1 and a 2. 1. How many change between a 2 and a 3? 1. How many change between a 2 and a 3 and a 4? 1. How many changes between a 4 and a 3? 1. So on a gray code, these are for high speed count. No matter which way you count, you're only going to have what? One bit change. So this will be something that you would have to really take in consideration if you have a PLC. I don't know of any PLC that counts in gray code. But if you understand gray code, your PLC is a computer. What can you do? You can take a gray code count and convert it over to a watt. So that's very easily, in fact. So this would be a gray code absolute count. Rotor. Are we okay? And this is the problem we have with absolute encoders. These bands you can't hardly see. This is the first band. So this guy here has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bands. So that's 1,024 count. See how close they get together out here on this band out here. Of course, the further that it is, the bands get bigger. The further you can valve, which is probably 2. But what's the advantage of an absolute count? Not necessarily. Yeah, we don't have to back it up. We don't have to keep up. We don't have to put batteries on this thing. We just got to do. We turn it off, come back the next day and turn it on. It's going to know exactly where it's at. So this is an absolute counter. So this is the actual one example of a detector. It's got all the photo detectors. But normally we do this with photoelectric. So all we do is we shoot a thing through them, through the thing, and then we have a detector, right? Larry says it's time for a break. Don't have to worry about keeping this thing powered up all the time. So the big guy we have normally is what we call incremental. So we have blades, or we have tracks, or we have stuff like that. And then all we do is just have some type of light source or some type of sensor. Usually it's optics, just sensing when these pedals come up. And then we actually have counters, external counters that do count. So this was an absolute encoder off a Hewlett Packard Prism.net. It kept up with the location of the paper. So the paper got fed in. How does it know how far to go to get it up to the print, right? You understand? Well, the motor that turns there got an encoder on it. It just pulses and the printer counts. And after a certain amount of counts, it knows the paper's at a certain position, right? No, this is motor. This is off an HP inkjet printer. And I already go get that. You can actually see the encoders on it. You got it up there. This was one that was donated, and they stuck it in a box, and it got tilted over. They didn't take it out. You got all that. It's got encoders on it. This is an old type mouse. Before we came up with the Optimax, what you did is you have what we call a trackball, and when you move it across the surface, it calls these encoders. Y'all see the encoder pedal? It's an X and Y axis. Now, when we move it across, we got some of these around here somewhere. The problem is that they would get goop inside of them, so you have to take them apart and clean them. Just moving around, if you goop, it gets garbage on the rods right here, and you have to take the apart and clean them all the time. So we had to clean our mice. So you go there and you start moving your mouse and it wouldn't move. All you did was it was set so you could unscrew it and get the balls out. People like the little rubber coated metal balls and they'd steal them all the time. Sometimes you move the mouse and would do anything, you turn around and the trackball, another one stole the trackball. And now we go to optical, which basically works on the same principle, but it picks up literally grains in the surface that you're moving across, decide how to do it. It's pretty, they're a lot smarter than you. So basically, to determine direction, we have two sensors that are offset. So depending on which direction it turns, you get pulses off its center. So this would be counterclockwise. So what happens? We go 1, 2, 1, 2. If we turn it counterclockwise, it goes what? 2, 1, 2, 1. So depending on how the counts come off, we can tell which direction the encoder's moving, which would tell our counters either to do what? Count up or count down. So now whatever we're trying to sense the position, we know the position it's going with no matter what direction. But we got to have what we call external count. So this is showing an encoder. This is the linear encoder. This would be a rotary encoder. And this is basically showing us how the things work. So if I did it the other way, it would count the other way, right? You understand? Pretty neat. Pretty neat animation too. But what's nice about here, we don't care about the number of revolutions this guy here makes. Right? You understand? What determines the distance you can move is how far your counters can count. So if we got a 10-bit binary counter, that sucker could count up to 1,024. Right? If we got 11-bit, it could count up to 2,048. If we got a 12-bit, it could count up to 4,096. So it depends on the counter. How far can this thing move? It's no longer depending on the wall, on the size of the encoder. What the size of the encoder determines is the resolution. How close can we get to what we need to count? Right? How accurate do we want to count it? Determines how far you can go. Yeah, it depends on the counter if you got a PLC. Of course, what they found out too, a lot of your PLCs, originally PLCs, the counters were not real, they were software. Now, one advantage hardware has over software is hardware is usually always faster. What was happening is we would bring these encoders into a PLC, and the PLC couldn't keep up with it. And so just about all your PLCs have what they call high-speed counters now, which are hardware counters built into the PLC. These are not software anymore, they are hardware. So they can count these encoders. You know, you got a motor running 1,700 RPM, 1,725. You don't want to do one count, you want to do multiple counts. So your motor might have 10 bands on it. If you try to use this, a lot of pulses per second. Your regular software count will keep up with it. But these guys have high-speed counters on them. The 1200s have high-speed counters on them, so all your DC PLCs will have high-speed counters on them. And these are actually hardware supported, right? So they're literally counters built into the chips on your PLC. Now the problem with these guys, what's the problem? Well, they're not absolute, which means if you turn them on, if you turn the system on, you lose your count. The PLC, you cut a PLC off, it keeps its program, but it don't keep its counts, right? So normally what we do on these is we have to start them from an origin. We have to start them from the same place. So this is why you got a dot matrix printer. You turn it on, what's the first thing you hear? You hear it reset. You hear it fine. So if the print head's out here, what does it do? It moves back and hits a photoelectric sensor on this side over here that says, okay, you're at 0, and from then on it can count the encoders, the incremental encoders, and has no problem at all. So this is the biggest problem. If we lose power to these counters, the counters are going to lose their power. So what do we need to do? We don't want them to lose the counters to lose their power. Back it up with a what? A battery. So your robots use incremental encoders, but they call them absolute encoders. But they're battery backed up absolute encoders. So the PLC reads the counters, but the counters is kept by what? Batteries. If you ever lose those batteries and you turn that robot off, you lose the robot origin. And that's when you got to know how to reorigin these robots. If you don't know how to reorigin, and the batteries go there. But normally, if you work at a plant that's got robots, they change those batteries. They should have a maintenance schedule to change those batteries out. Because power failed, even at big plants like USC. I was out there a couple of times when the power went out. That's scary when they got a peak in the Q box over there.
88. I was not up 88.
So this is kind of the basic circuit. So we have the incremental encoder, we have the encoder that just runs the wire. Okay. The problem is counters or electronic circuits. Electronic circuits don't work. So this is like you go out to your car and you pull your car battery. What did your radio do? All your preset stations, right? You don't understand. And that's basically what just happened. What you have to do, you have to go back and reset. Yeah. So if you had incremental encoders, you would have to put that back in an origin position. And that's what we have to do on a robot. So normally your robots either use the jig you put on there, or it tells you where to position it at, or it's got marks on the robot that says put it back in this position, and this is the zero or the origin position. We'll go look at some of the robots. Battery backed up incremental encoder. Used a lot. Why? Because man, you're not worried about the number of turns. You just let these suckers spin. Your counters keep up with everything. As long as you don't exceed the range of your counter, you're okay.
So is the basic
Well, no, because we have pots, we have different types of position sensors that are not encoders. So encoders are digital. They're digital position sensors. Where then your other position sensors are probably going to be what? They're going to be analog. So when we talk about, it is a position sensor, so all of them are classified as position sensor. But when we use the term encoder, it usually means what? Digital. But we could say position sensor and it would still be correct. Make sense? It's just like a limit switch is a proximity sensor.
Right.
But normally we have limit switches and then we have proximity sensors. Proximity sensors are usually solid state and digital mechanical. Limit switches have been around so long. I don't know what one got. It's like the first operating system came out for these computers. Originally they were built in, but then they decided the operating system for the computers needed to be loaded off of this, and that way you could change operating systems. And they called it a disk operating system. They called it what? DOS. Well, every operating system since then has been a disk operating system. But we call it DOS, and then we call them Windows 95, Windows 2000. So it's kind of, they was putting dates on them for a while, but then they dropped the dates because that was antiquated. So now they went back to version numbers. Right? The first DOS was the first Windows was not, it was a parasite operating system. It actually lived on top of DOS. You had to boot DOS first and then load Windows on top of it. So the first Windows was not a true operating system. We called it a parasite system. But we already looked at this. Very easy by offsetting those encoders, those receptors, on determining which direction to go. And then all it does is tell the counters to count up, count down. Let me go on our next break. Now, I threw this in here. So what robots use is they use incremental encoders. But to the controller, it appears like they're absolute. Because the counters and everything are out there with the encoders. And they put batteries on them. So the robots have batteries. What they're in there for one purpose, is to keep the count on those logs. On those counters. Those batteries go dead. You turn that robot off. You've lost the origin on the robot. None of your programs are running. Because why? They don't know where it's at. It don't know where it's at. Right? So that would be like me giving you directions. Saying go to the 5th red light and turn right. Go to the 4th red light and turn left. How many situations does that fall into? A lot. Unless I say, okay, from the gate with the red light, turn left, go down 4 streets and turn right. Now I gave you a point of origin, so now my direction comes in. And that's all your programs do. That's all a robot program does. It stores positions relative to an origin. If you lose the origin, then programs will run it. Normally you can still manually move the robot because you're looking at the robot, right? But you can't run programs. So they call these battery backed up absolute encoders. It's kind of a misnomer. You'll find that a lot in the industry. I was watching a movie last night and they threw out the phrase ISDN, but they used it in totally the wrong context. Like the movie Scorpion, the TV show Scorpion, I can't hardly watch that. You ever get to the point when you know so much these movies are just stupid? This is called a linear differential, linear voltage differential transfer. What determines how much voltage you get? So a transformer consists of 2 parts, right? What are the 2 parts? You may know. Yeah, we have a primary, and then we have what couples through is called what? Secondary. Now, how much voltage you get induced into that secondary depends on certain things. It depends on the ratio. One thing that depends on the ratio of the term. There's another very important feature. We refer to it as the coefficient of coupling. How close can you get the windings on your primary to the windings on the secondary? And then, how good can you couple the magnetic field between the primary and your secondary? This is why when you take transformers apart, you see that the primary and secondary sometimes are actually wound right on top of each other. They call what they call an E-core. And then they're wrapped around metal because metal concentrates magnetic field. So what we're doing here is we're not changing. So in the center we have a primary, and then we have 2 secondaries. And we're moving a chunk. So what we're trying to set position of move the chunk of metal, which changes the coefficient of coupling between the 2 secondaries. Make sense? Now one is wound in one direction. So notice this one, the outside, this one, this is the outside. If they were wound in the same direction, then my 2 outputs would be on the left. But here it's on the left, here's what? On the right. This secondary is going to output one phase. This secondary is going to output another phase. Don't understand? And what happens is when that rod moves, if it moves towards secondary 2, then the output of secondary 2 is going to go up, and the output of secondary 1 is going to go down. If it moves towards secondary one, then the output of secondary one is gonna go up, and the output of secondary two is gonna go up. And then they subtract them from each other. That's all they do. So secondary one is putting out 1 volt, secondary two is putting out 2 volts. Then the math would be 1 volt with the phase of secondary two, right? So if the output of secondary one is more, then it's going to give us a voltage at the algebraic sum of the two, but it's going to be the phase of secondary one. So what they can do is tell the position by the amplitude, and they can tell the direction by the what? By the phase. These are called linear differential transformers. Linear voltage differential. They're very, very rugged. They fill them up kind of like a shock on a car. They can be used in very, very harsh environments. Car shocks, they have a rod that moves in and out right, and they sell them up real good. And we run most of them in extremely harsh environments. These guys here can run in extremely harsh environments, but they're limited in their range. All position sensors, by the way. So this would be a linear differential transformer. These are basically, they look like shock. Basically what they look like. So you clamp the cylinder down to something. And then you hook that rod up to what you want to see, right? And these are LVDs. Use a lot of these. If you see something out there that looks like a shock absorber, something that's moving, and odds are that's a rod. That's an LVD. Of course, to see this, we would have to get up to the source. Unfortunately, we don't have to do that. So these are the only position sensors that we're going to look at. This is the electronics, which don't interest y'all a lot. This is a linear optical encoder, by the way. So we have those. They work on the same principle. This is a pretty good example of both linear and rotary, right? The HP object trainer we have built together. Shop over there. Well, we're gonna go over there, so I might go over there and find it. I'll show you that. Go over there. So any questions on these positions? So these guys here don't really have a transfer function that we got to figure out, right? Basically, that's not exactly true. What we go from a position to a count. You understand that? So what is a transfer function? It's the ratio between the physical quantity we're trying to measure over to what we convert it. So we're going to take a physical quantity, we're going to convert it to a current, or we're going to take a physical quantity and convert it to a voltage, or digital, we're going to take a physical quantity and convert it over to a number, right? That makes sense. And of course, if all we need to do is know when something's at a spot, or when it's at a position, or when it's this, then we don't have to use analog, we can use digital. Make sense? Any questions? A transfer function is when we take our physical stimulus and convert it over to electrical. And what can the electrical be? It can be analog, or it can be digital. So analog is we're going to take a temperature and convert it to a voltage. Or we're going to take a temperature and we're going to convert it over to current, right? Those are the two main quantities we use. Are we okay? Now, when we go from digital, we're going to take a analog quantity or a quantity converted over to numbers. Right? What comes down this way?
That's pretty cool.
Fast. That's one thing that's hard to do. Especially if you ride an open face helmet in the rain.
Oh. Yeah.
That's rough.
Help you.
And then plus your bike gets so dang dirty, so hard to clean because it gets everywhere, like everywhere.
You're gonna put this PowerPoint like.
Yeah, you won't have any animation.